All right. Good morning and welcome, everyone. Welcome back to Kids Week 2022 at the Intrepid Sea, Air, and Space Museum. How are we doing this morning? All right. The enthusiasm, and hello to everyone tuning in from home as well. We're so glad you're here with us. So everyone, we are so thrilled to welcome you back here on site yet again for another Kids Week festival this year. My name's Alicia. I work here at the Intrepid. And guys, if you didn't already know, the Intrepid is home to a number of really amazing things all year round too. We've got 28 of the world's coolest planes. We've got a Cold War era submarine right outside that you can go through and explore. Also upstairs in our space shuttle pavilion, we have the Space Shuttle Enterprise, a very, very cool space shuttle. It's huge. And also right now underneath it, we've also got a full-scale model of the Mars Perseverance rover and Ingenuity helicopters. Have you all had a chance to go see those yet? Yeah, absolutely. Check it out before you leave today. They're only going to be here through June, so make sure you come check it out. And that goes for you guys at home as well. So everyone, we have so much fun stuff going on all year round, but of course, Kids Week is such a fun time. We have so many wonderful vendors here today, so many wonderful partners, Billion Oyster Project, Future Change Makers Academy, all these fun things. But everyone, I am here today now to introduce you to a very good friend of mine. This is Jonathan Millard from our Intrepid Education Department. Everyone give a round of applause for Jonathan. Yeah. Great way to wake up this morning.
Yeah,
a round of applause. And everyone, he's here and he's going to be doing a very interesting demonstration now on how we launched the space shuttles. That again is that big white thing up in our space shuttle pavilion. How did you get something like that off the ground, right? He's going to tell you how. All right. Pass it over to you, Jonathan. Right. Have a good time. Have a great Kids Week.
All right. Thank you so much, Alicia, for that great introduction. Hello, everyone. Again, my name is Jonathan. Thank you so much for joining us today. So today we're going to be talking about the space shuttle. So has anyone just raise their hand if they've seen the space shuttle already today? Oh, so some of us have seen that space shuttle upstairs. It's upstairs on the top of the flight deck in a very big building, the Space Shuttle Pavilion. And when you see it, you're going to see, wow, this is a really, really large object. So what's interesting about that space shuttle that we have, it's Space Shuttle Enterprise, the very first space shuttle orbiter ever created. Only 6 of them were made, and it's the very first one. But something a lot of people do not know about the space shuttle upstairs, that it actually did not go into space. It was like the first draft of the space shuttle program where NASA was trying to figure out how they can send something so big up into space, but then have something glide down and land on the Earth, almost like a big paper airplane. So let's investigate. Oops, this a little bit. Let me see if my slider is working. Oh. Let me see. I might ask. Yeah, tech support really quick. Can we give an applause for tech support? Thank you so much while we're trying to figure that out. Yeah, so we're going to talk a little bit about the space shuttle today. And the space shuttle orbiter actually had to glide down. So a big test for these space shuttles was putting them on top of a very large aircraft called a Boeing 747. And with that Boeing 747, the space shuttles would have to release from the top of that and glide down. So it would be about 26,000 feet up in the air. And they would drop and release and go about 470 miles per hour as it's gliding towards the ground. And astronauts inside of these space shuttles said it was almost like riding your favorite roller coaster, but then having to park it, which is really interesting, right? So who here has flown a paper airplane before? Okay, great. So can paper airplanes just keep flying and flying and flying on their own? Give me a thumbs up if they can just keep flying and flying on their own. Thumbs down if we don't think they can do that. Yeah, most paper airplanes can't, right? Thank you so much. Give tech support another round of applause. Thank you so much. All right, so these paper airplanes, once you throw them, they just go down to the ground. So that's what these space shuttles are doing too. And what we see here is Enterprise being tested on top of that Boeing 747 being released so it could glide down. But how did we get to this point, to testing these space shuttles, to having space shuttles blast off up into the sky, going up to 350 miles above the Earth's surface, and even going 17,500 miles per hour as they orbit around the Earth? How do we get to that point? And that's what we're going to try to figure out today. We're going to do this by talking about Isaac Newton's laws of motion. So some of these may be familiar to us, some may not, but we're going to talk a little bit about them today, and then we're going to have a fun demonstration to learn a little bit more about them. So Isaac Newton's first law of motion is the law of inertia. So it's an object at rest is going to stay at rest unless acted upon by an outside force. An object in motion is going to stay in motion unless acted upon by an outside force. A way that I like to think of it is I have a lot of trouble waking up in the morning, okay? Sometimes I actually just fall asleep while talking, all right? But hopefully we won't see that today. But when that happens, I need like an outside force to wake me up, maybe like a loud noise, maybe an alarm. Well, oh, wow. Okay, sorry. Like I said, sometimes when I'm just like talking, I just fall. Okay, thank you. Thank you so much for being that outside force to wake me up so I wasn't at rest anymore. That's kind of how objects are too. If an object is at rest, it needs some type of force to get it moving. And if an object's an object's in motion, it's going to keep moving unless an outside force affects it. We're going to talk about that in a bit. And then we have our second law of motion. That's force equals mass times acceleration. And what that means is it means a few different things. That in order to move or accelerate stuff or mass, we need to apply a force. That's one way to think about it. But also these things are related. So if you change amount of mass, maybe we'll see more movement. If we change the amount of force, maybe we'll see more movement if the mass is the same. And we're going to explore that in a bit too. And our last law of motion is for every action, there is an equal and opposite reaction. There we go. For every action, there's an equal and opposite reaction. So the way I like to think about this is when I swim. I'm not the strongest swimmer. This is how I swim. I just do this, okay? So when I swim and I'm doing this, I'm pushing water backwards. I'm pushing water backwards. What direction will I go in if I push all that water back? Can you point in a direction for me? What direction? If I'm pointing all the water back, I'm going to go forwards. There's an opposite reaction there. I'm pushing all that water back to go forwards. So let's investigate this with these straw rocket launchers that I have over here. So over here, I have some straw rocket launchers. And the way they work, I pull this lever back and release it. And when I release it, air comes out of this tube here. And right here, I have two straws. I have a red straw and I have a blue straw. And something I'm noticing is there is less clay on the red straw. There's more clay on the blue straw. Can you point to which straw you think is heavier? Less clay here, more clay here. Which one do you think is heavier? Okay. Which one? Yeah, okay, so we're thinking maybe this blue straw is a little heavier. Okay, so I'm going to put our straws on our straw rocket launcher here. And I'm going to pull them back so we might see something happen, okay? So right now I'm looking at these. Are these straws moving or are they at rest right now? They're at rest. They are not moving right now. We need to apply an outside. Oh, okay. Oh, thank you so much. Thank you so much for that outside force. Okay, so we have to pull these. Okay, thank you. We have to pull these back and we might see something cool happen, okay? So right now I'm going to pull the straw back and, but I'm noticing something here. There is clay on top of this straw. That means when that air is trying to go up, it's going to get pushed down. It's going to get pushed down. So if we're pushing all that air down, what's the opposite reaction? We might see these straws go up. Okay, so right now we're doing a little bit of rocket science. So whenever we do a little bit of rocket science, it's good to have a countdown, okay? So we're going to say a countdown from 3, 2, 1, and then say blast off, okay? So let's do this together. 3, 2, blast off. Okay, so that moved a little bit up, but I want it to move a little higher, all right? Well, that wasn't that impressive to me. But what about this red straw? So we said, which straw did we say was heavier? The blue straw. Okay, but I've noticed there's less mass on this straw over here. So what do we think? Do we think this is going to go higher than that straw? Or do we think it's not going to go as high? Give me a thumbs up if you think it's going to go higher. Thumbs down if you think it's not going to go as high. Okay, interesting. So let's see. Okay, I'm going to need another of those countdowns. So 3, 2, 1, blast off. Okay, so 3. Wow, and that went a lot higher. Why do we think that red straw went a lot higher? I see some hands raised. So if I call on you, just say it loud and proud. My friend over here. Oh, so because it has less mass on it. So I'm looking at these straws here, and there's less mass. We use the same amount of force for those straw rocket launchers. Same amount of force, but because there was less mass on the red straw, it accelerated more. It was able to go a lot higher and a lot faster. That's really interesting. So we're going to talk a lot about mass today because space shuttles are quite massive. They have a lot of heavy things attached to it. So over here, this whole entire thing that we see here is what we consider the space shuttle. Just this part, this part over here is considered the space shuttle orbiter. That's what you'll find upstairs. Okay? So just this part over here, this white orbiter that we see here, that weighs about 150,000 pounds. Or 68,000 kilograms, okay? But then something really interesting about space shuttles is they can carry things inside. They're like big space trucks and can open up. So people go in the front and really cool things like satellites and telescopes and even parts of the International Space Station can fit inside. Can you thumbs up if you've ever ridden in a school bus before? Has anyone been in a school bus before? Okay, yeah. So your school bus could fit inside of the space shuttle. So that's it. Definitely take a look at it later. It's very, very big. So that can hold about 65,000 pounds of stuff inside, or 30,000 kilograms. That's a lot. But now I'm looking at all this stuff attached to the space shuttle. I see this big liquid orange fuel tank here. That weighs 1.6 million pounds, or 725,000 kilograms. All right, and then I'm noticing these solid rocket boosters on the side here, these white solid rocket boosters, and those weigh 1.3 million pounds each, or 590,000 kilograms each. That's a lot. That makes the space shuttle a whopping 4.4 million pounds, or 2 million kilograms. It needs to blast off and go all the way up into space. Do you think this is easy or kind of hard? I think that's kind of difficult, right? So it's really interesting that NASA was able to figure out a way to do this. And the way they're able to do this is with a lot of fuel and a lot of fire, okay? So what we're looking at here is a space shuttle launch, and we're seeing something ignite, and we're seeing a big plume of smoke on one side and a big plume of smoke on the other side. Because there's a lot of fuel being ignited, helping the space shuttle blast off up into space, putting a lot of energy downwards so these space shuttles can go up, right? That equal and opposite reaction. So let's talk a little bit about this, okay? So how do you get a controlled explosion to send something big like this up into space? And for all my junior arsonists in the crowd, all right, this is some information for you, all right? So to make a fire, to make an explosion, you need a few things. You need fuel, you need an oxidant or oxygen, and then you need ignition. And then when you put these three things together, you generally get fire, okay? So I'm going to do this in a way. I'm not going to create fire. I'm going to create a really interesting reaction, though. So what I have here are thermite spheres. And what they are two iron spheres. But one is wrapped in something. Can anyone tell what this is wrapped in? I know it's a little far away. My friend here? Okay, so aluminum foil. Was that what you were going to say too? Aluminum foil? Yeah, so we have aluminum foil wrapped around this iron sphere. But this iron sphere doesn't have any foil wrapped around it. But I'm noticing there's a little bit of orange on this iron. So if I see orange or red on iron, what does that tell me? See orange or red on iron. My friend over here, say it loud and proud. Say a little louder. So it's hot. Oh, maybe it could be hot. Oh, yeah. So when you heat metal up, you can see it be hot, red sometimes. Yeah. Okay, maybe fire too. Sometimes I see it not when it's hot. My friend back here, say it loud and proud. Oh, yeah, rust. Maybe there's rust on that iron. So there is a little bit of rust. And what happens to iron when it gets rusty? We say it's oxidized. So we have our oxidant over here, and we have our fuel over here. Now, all we have to do is add some ignition, and then we get, oh, let me try that one more time. A reaction. All right, so you add those three things together, and that's what's happening with the space shuttles, using these three things to blast off up into space. Am I on fire? No? Okay, good. Just checking. All right. So what we're looking at here is the liquid fuel being burned. So the liquid fuel inside of this tank, it's actually liquid oxygen and liquid hydrogen. So liquid oxygen and liquid hydrogen, where do I normally see or hear about liquid hydrogen and liquid oxygen? Maybe 2 parts hydrogen, 1 part oxygen. Has anyone heard of something like that? Yes. Water, yes. So as this liquid fuel is being ignited, it's creating 3,000 pounds of water pushing down per second, creating 375,000 pounds of thrust, helping the space shuttle go up into the sky. But then we have solid rocket boosters on the side here, and inside is like a gummy-like aluminum. And when that is burned, each of these creates about 2.6 million pounds of thrust, helping the space shuttle go up into space. So it's a lot of thrust being created and pushing a lot of things down to help these space shuttles go up. Okay? But something interesting happens about 2 minutes into the space shuttle's flight. What do we notice? Oh, yeah, we even see a little bit of fire there, too. What do we notice happen about 2 minutes in to the space shuttle flying? Yes, my friend here? Yeah, so these solid rocket boosters fell off of this space shuttle. So why do we think the solid rocket boosters fell off? Why do we think the solid rocket boosters fell off? My friend here? Oh, yeah, because maybe that extra weight that was carried was making it go down. Anyone else have another idea? Yes, my friend here? Okay, so maybe we're thinking about that water kind of blasting off. And my friend over here, yeah? Yeah. Okay, so maybe it's empty. Maybe we don't need that fuel. So these are great ideas. So all that fuel was expended. We used all of it going up into space, but we don't want to carry that extra mass around. So we release it. But something really interesting happens as you release that mass as it's going up into space. And I want to show this with another straw rocket launcher that I have. And this one is a bit bigger. Okay. So here, I have a pretty large straw rocket launcher, and maybe I will do it not so quite underneath this duct here. So here I have some straws, okay? I have 3 straws. So imagine this almost like the space shuttle going up into space. So I'm going to bring this down onto my straw rocket launcher, and I'm going to release it. So again, I need to count down that 3, 2, 1, blast off, okay? 3. All right, so we noticed it went pretty high, but I want it to go a little higher. So what do you think I could do to make this go higher? If that's the most amount of force I can create, what can I do to make it higher? My friend here in the red? Oh, maybe get rid of some of those straws. Get rid of some of that mass. Okay, so I'm going to get rid of some of that mass. And let's see what happens. And now I only have 2 straws. Before I had 3, now I have 2. Okay, so I'm going to raise this up. I'm going to need the 3, 2, 1, blast off again. 3. Wow. All right, we saw it went higher, and I think I lost those straws, but don't worry, I have more. It's on top. Someone will have to get that later. All right, thank you. Okay, so let's do that one more time, because that was 2 straws. We saw how high it went. I'm a little, wait. Okay, thank you. Yeah, okay, so I'm a little crazy. I think I want to actually just try this with 1 straw. What do we think is going to happen? It's going to go really, really high up. Okay. Might touch the ceiling. Okay, maybe it'll get stuck to the ceiling. Let's see what happens, okay? All right. I'm going to need one last countdown, okay? So 3. Whoa. Awesome. All right. Thank you so much, everyone, for that wonderful countdown. So we noticed as we were reducing that mass that the straws were able to keep going higher and higher and higher. They're accelerating more and more and more. And that's what's happening with the space shuttles. So at this point, the space shuttle is about 17,000 miles per hour. Space shuttles want to get 17,500 miles per hour to just keep orbiting around the Earth and just moving with Earth's gravity and getting pulled around the planet. So we want to get to that speed, 17,500 miles per hour. So about 8 minutes into the space shuttle's flight, something else happens. Can anyone guess what might happen next? Yes. Okay, so maybe it's going to move around in outer space and we might see something else happen, my friend here. Okay, maybe we'll go in a minute. So space shuttles didn't actually ever go to the moon. Its moon is way too far away for space shuttles. The most space shuttles have gotten is 350 miles away from Earth. The moon is 240,000 miles away, but they still go pretty high. But I'm noticing that the liquid fuel tank just fell off of the space shuttle. So the solid rocket boosters, when they come off of the space shuttle, they have parachutes and they land back towards the Earth. This liquid fuel tank starts to burn up in Earth's atmosphere and burns up around the Indian Ocean. And then because as it's coming down, there's so much friction, it starts to burn up. So you don't have to worry about really big pieces. But the solid rocket boosters are used again. So now this space shuttle is almost at 17,500 miles per hour. Almost. But it needs a little bit more of a boost. And the way it creates that boost is with these areas on the side here. So it has something called orbital maneuvering systems that help the space shuttle move around in space. And inside here, you're going to find another type of fuel. And this fuel is called hypergolic fuel. So we have a fuel and an oxidant. The fuel is monomethyl hydrazine. Can we all try saying monomethyl hydrazine? Great job. Okay. And then we have our oxidant, dinitrogen tetroxide. Monomethyl hydrazine? Dinitrogen tetroxide. I can't even say it. Dinitrogen tetroxide. All right, it's really hard to say. Try saying everything really fast. Monomethyl hydrazine dinitrogen tetroxide. Okay, so it's kind of hard to say, we're realizing this, all right? But it's also very hard to work with. These chemicals are very dangerous because if you put these two things together, you get a very complicated formula, but you also get spontaneous combustion. If you put these two things together, they explode on contact. So I said to make an explosion before, we need fuel, oxidant, ignition. In this case, we just need that fuel and that oxidant, and they're able to create explosions. And this is very handy to have in space when you're kind of worried about having access to oxygen and fire working well. So if you can control that explosion, you can help that space shuttle maneuver around easily. So the space shuttles use this. If you go upstairs to the space shuttle pavilion, you're going to see these different areas where that hypergolic fuel would be used on the space shuttle. And that's what helps the space shuttle move around. And this is what the space shuttle uses to come back down towards the Earth and glide back down like a big paper airplane. And what we're looking at here is very special because this video is the very last video of a space shuttle ever being used. Space shuttle stopped being used in 2011. NASA is instead working on something else instead of using space shuttles. And what NASA is working on uses the same type of the liquid fuel that the space shuttles used. It's also using the same type of solid rocket booster technology the space shuttles use also. But it's going to be used in a rocket format instead of this space shuttle format. What NASA is working on now is something called the Space Launch System. And the idea behind the Space Launch System is that NASA wants to return to the moon and wants to send astronauts all the way to Mars. And this technology wouldn't be possible with a lot of the insight learned from space shuttles and all that knowledge that we discussed today. So that is the end of my demonstration. Thank you guys so much for joining me today. Thank you. Thank you. And I'll be down there with a mask on if anyone wants to ask me any questions. All right, thank you so much.
Right, another round of applause for Jonathan from our education department. Thanks so much for that explosive presentation. Wasn't that so much fun? Love to see those sparks. Thermite Spheres. Thank you, Thermite Spheres. So everyone, if you enjoyed that, just so you know, our education department actually does programming on site here as well as virtual programs. And we've got things for pre-K through 12. We've got things for after school, for teens, for seniors, you name it. We are happy to provide it. So if you're interested, check out intrepidmuseum.org/education. Also, don't miss out on our Maker Zone right over here. Earlier, they were making rotocopters. Later on, they're going to be making robotic arms. So if you're interested in that, definitely check it out. You can make your own robotic arm to move something in space. And of course, don't forget to see our actual space shuttle right upstairs in our space shuttle pavilion. Really, really amazing site. And, you know, very important. It's the prototype orbiter, as he was saying. Now, so everyone, if you are interested in more explosive demonstrations, do not forget to join us at 1 p.m. where we are going to have a very special guest here from Mad Science. They're going to be doing a show called Mad Science Spin Pop Boom. So you are going to be able to witness some amazing feats of chemistry right here on our stage. All right. So come right back here at 1. That goes for everyone tuning in at home as well. And have a wonderful rest of your Kids Week, everyone. See you at 1 o'clock.